To review just a bit, we have the arc, which I call the arc of process, going through 4 levels, and this important point, the turn. Now the turn, perhaps the simplest way to start is to say it's an extra dimension. I call it zero dimensionality, but it's a freedom that the entity has by virtue of the fact that it started with pure freedom, but it's now under complete constraint. That is to say, it's fixed in space and time, but it can still choose. It can still rotate in the sense that it decides on a different goal. It's as though you were in prison, you're restrained, but you can change your mind and decide, well, figure out the situation instead of continuing to do the things that got you in prison. This is the most interesting part of the whole thing. But it still can be done in quite a scientific way. Dimensions normally mean, that is to say, to the scientist, a dimension is a variable to which you assign a value. And the idea that you could have a dimension of just rotation was only introduced by Eddington. Eddington describes it as the phase dimension. He does not associate it with choice, but he uses the phase dimension to show how you can reconcile the problem that Einstein is reputed to have not been able to solve, the reconciling the relativity theory with quantum theory. This is pretty heavy, but it'll be easier later. I'll just say it. Eddington realized that the curvature of space-time, which is what the relativity theory introduces, is the same as the rotation that's implicit in the photon, the rotation implicit in the quantum of action. It's just a question of the length of the cycle. For the photon, it's very, very short. For the universe, it's very, very long. But this rotation is the same thing. Now, what is rotation? The way it's represented mathematically is by the circle. And pi is the universal symbol for the circle. It's really an angle that turns all the way around. Forget about the diameter of the circle and think of just the fact that it's an angle, which can have any value. And it's that circle, that rotation, that makes the physical universe. This great sweep of things, and you can think of all the possibilities, that direction, that, and that, as well as up and down. In 3 dimensions, of course this is in 2 dimensions, but if I rotate this around its diameter, I make a sphere. So the pi that's characteristic of the plane, or that becomes characteristic when you have a plane, also carries over into the 3 dimensions of the sphere. But you could ask yourself, well, why is it not more complicated in 3 dimensions than it is in 2? That is a very pertinent question, because actually the sphere is a special case. If I'd chosen to rotate the circle, instead of rotating it around its own diameter, if I'd chosen some other diameter or some other point, say out here, and rotated it, I'd get a figure that makes a donut-shaped figure, like an automobile tire. In other words, there would be two pies and they'd be separate. Can you see that? I suppose if I do it this way, if that filled in a solid figure, it would be a donut shape, automobile tire shape, with a hole in the middle. That, the value of the volume of that would be pi squared, because there are two pi's. And this has strong appeal as a model for a theory of process, because in addition to space and time, we've now given it this extra freedom, this freedom of turning, in the case that I've illustrated, this way, but it could be either one. And that other turning gives it a chance to come back to what it was originally. For that purpose, I can illustrate it better with this donut-shaped figure, which is called a torus, which is circular, as the thing I indicated, in two ways. It's circular this way, and it's circular this way. And actually, if the whole were infinitely small, the diameter of the two circles would be the same, because the central circle, the inner circle, would be that, which is the same diameter as this. Now, when you get a figure of this sort, you get into a subject known as topology. That is the science of surfaces. And something very interesting happens. One of the things that happens is that the coloring problem becomes more complicated. To make a map on the surface of a sphere, that is to say on the Earth's surface, for example, only 4 colors are needed. You couldn't make a map such that however many countries there were, it would not be possible to distinguish the countries by no more than 4 colors. In the case of a torus, shaped like the one I'm holding, 7 colors are required. And I'm going to show you this because it's colored in 7 colors. And if you look closely, you'll find that each color is beside one other color. Now notice the blue, for instance. One side of the blue is the gold, and the other side is the purple. This side is green, this side is red, but there's also some yellow, so that there are 6 colors around the blue. The same applies to the yellow. There's purple, blue, red, orange, green, and gold all around the yellow. Now, the colors are essential differences that are possible in that kind of a universe. And we have here 7 different kingdoms. the basis for the theory is that those 7 kingdoms are the equivalent in terms of the distinctions of the coloring problem. So that the 4 things that were suitable distinctions for the physical universe, from light to atoms, then as soon as the turn comes about, have to be provided by 7 colors to represent those entities that can evolve, as it were, using the determinism that has been established at the molecular level. In other words, we're talking about a reflexive universe. We're talking about a universe that can create creatures that know they're in a universe and do something about it. To carry this a little further, I want to go back to the 4 elements. Recall that I put them in the order fire, water, air, and earth. Now the 4 elements have almost infinite ramifications, but a simple one that will illustrate their something to start with is the 4 seasons. For example, well, it wouldn't be an example of this. 4 seasons begin spring, summer, autumn, and winter. In spring you have the burst of activity that starts life going. In summer, the time of maximum growth. In the fall, when things are beginning to stop, and you have to think about what's happened, reap the harvest. And then winter, when you have to be careful with conserving crops and making it through the year until the next summer when you can get more food. Well, this gives an inkling of or an entree into a next step, which I call the cycle of action. Now this just shows the position 1, 2, 3, and 4. You could think of this spring, summer, autumn, winter. But now let's think in terms of the cycle of action. An infant begins by reaching out, exploring its environment, touching things. And then it, let's say, touches something like the hot stove. It pulls its hand back right away, it hurts. Then it stops to think. And if you don't want to say the infant thinks, you can say he associates the pain with the hot stove. In any case, the 3rd stage would be association of the pain with the hot stove, and the 4th stage would be avoidance of the stove, being careful. Now, this is the pattern in any learning cycle. If you were to learn to drive a car, you would begin by pushing levers and things and finding it was the wrong one, then seeing what you did, and finally being self-conscious and careful. But after you'd been self-conscious and careful for a while, it would become instinctive, and you could begin again on a new cycle. And once you've learned to drive the car, then you could learn how to have an argument with your wife or something while driving, and have a learning cycle on a larger scale. So the learning cycle is again a reflection of these 4 stages. And as we normally employ the learning cycle, we go through it many, many times during a lifetime. After we've learned to avoid the hot stove, and then we learn to walk, and then we learn to talk, then we learn how to spell words and make sentences. There's almost no end to the number of things we have to learn in order to live, but always piling on what we had before, so that the steps that were once self-conscious become instinctive. And let's say someone's composing a message or a letter on a typewriter, they're employing all kinds of automaticities to do this task, at the same time choosing what they're doing somewhere in their head. But if they decide to write a sentence, their hands find the right places and spell the words correctly and make the right spacing. It all seems very automatic, but this automaticity is based on a hierarchy of separate systems that are organized. And that's just what we're dealing with in the whole arc. Well, what happens at the turn? Normally this would go on, taking on larger and larger tasks, maybe learning more and more, first going to school, then going to college, then getting a degree. It may go on indefinitely. But at some point there can come the turn when you decide to use what you've learned so far rather than build up more. We have that predicament with our military. They're always trying to get better and better weapons. But of course the other party always gets better weapons too, so then they have to get still better weapons. And, well, you've seen all that occur. They haven't yet made the turn. The turn would come when they realize that this wasn't getting anywhere, and they better forget about the weapons. The Chinese, incidentally, I think it was about 1000 A.D., invented gunpowder long before we did in the West, but they decided not to use it for weapons. Well, suppose you do decide not to keep on getting more and more of whatever it is, then you would have this picture. Reaching point 4, instead of moving on into a new cycle where you got into new kinds of trouble, you use what you have and retrace your steps. This, the example I use in the book is the fisherman who's run out of food and uses his last little piece of bacon to catch a fish. He is reversing the normal instinctive action and being circumspect, and begins to employ the cycle of action to get out of the difficulty he's in, which is lack of food, by baiting the fish. And this would be catching the fish and I suppose eating it. Well, now the reason for using this representation is principally to show the same principle that the turn does, but in a different language. We don't want to get hung up on one interpretation. See, the V here says it's a turn, but it doesn't make explicit what's going on in the sense that this does. This gives the turn in different terms. Recall that this 1, 2, 3, 4 are the 4 levels. It started at 1, 2, 3, 4, and at 4 turns and goes back. Now this turn is also the other pi of the donut. In other words, the thing that was concealed here becomes available when you use it this way. And available, that is, to use what's learned to build, you could say build a ladder, but it's really building a system that will enable you to get to your goal. Now let's see. Let's check back and see if we've got all this. We have the turn. The turn involves the introduction of a new pi. The pi involves changing from a sphere to a torus. And the ascent, it now becomes apparent, is a regaining of the freedom that was lost on the way down. And I could go, if you can recall that chart, you recall that the plants became free in time, the animals became free in space, and I would say man gets back the complete freedom by having no limit to the goals that he can choose. That is, the goals could be beyond his own lifetime. Now, before we go on, I want to make one more step with this arc. You see, I've taken an example. Of course, it's a rather large example. It's the whole universe. And these are the divisions. But in general, we want to be able to give rather abstract designations to these different stages that will make them applicable to any process. And rather than use the words particles, atomic, I use the word that characterizes their function, their power. So that rather than call this purpose, I call it potential, because it has the potential attribute. Particles, I could either call it attraction. It seems to work out better to call it binding, because the result of attraction is that things are bound together. In the case of atoms, I call it identity. You recall that the atom is the first one to have an identity. And incidentally, that identity, why does the atom have an identity that the electron does not? It's because the atom has a nucleus that doesn't participate in its interactions. See, the atom is a proton, or a number of protons in the nucleus, surrounded by electrons running around the nucleus. And in order to interact with other atoms, it either gives up or takes on more electrons based on this principle of attraction. But when it loses an electron, it would seem that it would become another atom, because the atoms are distinguished by the number of electrons in their outer shell. So if you suppose you had one with 6 electrons in the outer shell and it gave up 1, then it would be like an atom with 5. But in this case, it has its own identity. There is a charge on the nucleus that tells it what it really is, so that it knows how many electrons to get back. This brings out that identity is based on having a center or core that doesn't change and is not influenced by the interactions with its other partners or with its environment. So again, the principle of identity is indicated by this circle. For molecules, I make the key word combination because it combines the identity with the binding of the 2 and 3. For plants, this key word is the power that the plants have of growing. Call it the power of growth. For animals, it's the power of mobility. And for man, I took the word from the biblical account, dominion. God gave man dominion over the beasts of the field and so forth. Now with those key words, I can introduce the next step of this whole unfoldment, which is to say that each of these stages itself has substages. And this brings me to what I call the grid. The grid is a display showing both the stages and the substages. And if you look in this left-hand column, you'll see light, particles, atoms, molecules, plants, animals, and man in a vertical array. And under the words for the kingdoms, you'll see the word that's the key word for that kingdom. Thus, for light, it's potential, for molecules, binding, for atoms, identity, and so on. Now, if you look in the top row, these, at the top of each column, is the corresponding word. That is, the first one potential, the second one binding, the third identity, the fourth combination, growth, mobility, and dominion. In other words, the rows, each row is one of the kingdoms, and the columns divide the row into substages, and the substages have the same key words as the corresponding kingdom, or stage. You could call it a stage instead of a kingdom. Now let's take a quick run through one of these, just to show how the principle works. For instance, let's consider the identity column. If I begin at the bottom, that is the row for man, and the equivalence of identity for man is having an ego. So the birth of the ego would come at that stage. Coming up one, the animal begins to know itself through having its stomach. The coelenterate is the first animal to have an organ, which is a stomach, to be able to say, this part of the ocean is me, because this is a sea-living creature. And the word coelenterate, incidentally, supports this because cell comes from the French coelum, which in turn from the Latin, it means sky, the circle of the heavens. And the entra is the entrail or stomach, so it's a hollow stomach. The corresponding thing for plants, the embryophyta. These are the first plants to segregate the embryo from the rest of the plant. See, the problem for the plant is growth. And at the beginning, it just multiplies its cells. But then at the third stage, it separates the embryo from the rest of the plant, giving the embryo an identity. The next one coming up this takes us into chemistry, but the non-functional compounds, which I'll be getting into shortly, are the first molecules to have an identity. When we come to atoms, we are it's the first row of the periodic table that has a circle before it. In other words, it's the third row, because until there is at least one ring of electrons, the atom doesn't have this centrality which makes it have identity. We're talking about the identity of the identity kingdom. And it's very interesting that it's these atoms in our own physical bodies, for instance, that retain their identity. For example, in the plant, the chlorophyll, it focuses around magnesium, and magnesium is in the identity row of the atomic kingdom, the identity column, I should say, the atomic kingdom. So magnesium is one of the first atoms to have identity. By contrast, the atoms that don't have identity, such as hydrogen, carbon, nitrogen, and oxygen, just become whatever you want them to become. In other words, you eat bread and it becomes flesh, or you eat meat and it becomes your DNA. The molecules that make up the molecules made of atoms having no identity provide the substance of the body and not the special functions, whereas the atoms that have identity make for the special functions. For example, iron has the special function of being the core of the hemoglobin in the blood. I can't tell you much about the upper kingdoms, except that this, in light, the atomic spectra are the way you identify substances by the lines from the spectrum. Now if we try well, let's see now. We could try any column, but I like the fifth, which shows very clearly. We're on the bottom now with the creative genius. We'll explain more about the genius when we come to him. But the annelid, which is just above, is the first animal to create a hierarchy of segments. The earthworm, which is an annelid, sorts itself out so that the head gives the order and the other segments carry it out. Each of us has this same hierarchy in our own constitution, because if we didn't, then the stomach might rebel and decide not to digest what the mouth had eaten. But in any case, the hierarchy in animals leads to creating a head. The head is near the mouth where decisions are made as to what to eat. The rest of the organs carry out the task that the mouth which eats has commenced by digesting the food and finally excreting it. In plants, we have these plants are the segmented ones. I think some calamites is one term, horsetails. They're segmented vascular tissue. If you haven't seen a calamite, then think of a bamboo, a series of segments, one after the other, through which the fluids are pumped by the plant. When we come to chemicals, we have the polymers. You can tell from the word polymer, polymer, that means many segments of the same principle is going on, a series of segments. These are chain molecules. They may be of any length. Plastics are a good example, but so too cellulose, which is a natural plastic, even the sugars. they can be very, very long, hundreds of thousands of units long, repeated segments of the same thing. They are called polymers. Remember, these were the metamers. The animals are metamers, the annelids, and the chemicals are polymers. I can't tell you about the atoms. They have see, most of the attention about atoms goes to chemical properties, but this would involve properties beyond the chemical properties, and they're still not known to science. But one of the things that I have discovered is that iodine, which is this fifth stage chemical, is essential to the thyroid gland, which rules growth. So it's very appropriate that iodine is in the growth column of the chemicals. Well, in similar fashion, the other columns, I don't need to go into them all, show that the same principles that were operative in the stages are operative in the substages. And the same keywords apply. Now, this has been especially useful to me in setting up this grid because it's rather like a crossword puzzle. The only trouble is it's a stale crossword puzzle now because I've filled in all the squares. I only wish you could have some of the fun I did filling in the squares before I knew what went there. There's one stage I knew that there would have to be a mobile chemical. Can you point it to the mobile chemicals, which are the proteins? I didn't know there was a mobile chemical. See, this is the mobility column of the chemicals. But it seems that St. Georgi had just discovered that actin and myosin, which are the chemicals that make up muscle, very important to our mobility, are themselves mobile. The chemicals themselves change their shape in order for the muscle to work. Now let's take one of these kingdoms and go through it in some detail. I think I can put this aside because we don't need it. But just to start with, let's take animals. Think, if you will, of what kinds of animals are there? I often ask the class this, and they'll say, well, bears and dogs and cats, lions, tigers. And then somebody remembers something, let's say, paramecia. Well, lions, tigers, bears, cats really all go together into one grand phylum. So you have to think of different phyla. Phyla is a grand division of the animal kingdom. And the rules of the game is you're looking for levels of organization of the animal principle. And certainly you can start with paramecia because that's only one cell. Animals more evolved than the paramecia will have many cells. So let's follow it through. One-celled animals would be the first stage. Then the principle of cell division occurs, or cell multiplication. So you have many-celled animals. They're called metazoa. And the first many-celled animals are the sponges. Now we do need the arc. We're down here. We went from the paramecia to the sponges. Now the next step is the identity step. We mentioned it before. The sponge doesn't know which is inside and which is outside. It's just soaking up the ocean and somehow getting nourishment from it. So the stage that creates identity, the coelenterate, is when the animal creates its own stomach, and actually the mouth and the anus are the same. It has an opening, but it draws the ocean in and then spits it out again. And sometimes they have little arms which reach out and grab small fish and things. They're very beautiful, and they look like flowers. Some of them are called sea anemones, others are sea lilies. But they're stuck to the ocean floor. They have no mobility. They are learning how to digest food, and that is really the task of the animal for the first 4 stages. Now the next step takes us to a rather large category, which I have to put many phyla together, because these many phyla are all the same level of organization. That is to say, we've proceeded now to many organs, and there are other things besides mollusks that have many organs. Flatworms, roundworms, starfish, squids, snails, oysters, clams. All of these are animals in what I call the 4th substage, having many organs. They have acquired the complete repertoire of organs needed for digesting food. So you might say, where do they go next? Well, their next step, as we said, was to organize themselves into a number of segments. These segments, variously called, well, they're mers, meta-mers, but the worms are called annelids. Annelid means a number of rings, and metamer means a number of segments, so it's really the same thing. The metamers organize into a hierarchy these organs that were developed in the previous stage. Now the next step is for the chain to have side chains, for the animal to grow legs. And we have the arthropods. What does that mean? Arthro, like arthritis, means joints. Pods are feet. So these are the creatures with jointed feet. Now notice that the foot itself is a chain. In other words, we have chains with side chains. And that, like the tree with branches, or the chemical with its side chains, is an extension of this chain principle. You see, we're in an even kingdom, and we repeat in the sense that the chain theme is recapitulated. Then the next, well, we better talk about the arthropods, because this includes all of the insects, but also spiders, crustaceans, that is to say crabs, lobsters, shrimps, things like that, and millipedes, centipedes, and there's one extinct form, the trilobite. All of these creatures have this multiplicity of legs. It goes from millipedes to centipedes to decapods, which are the crustaceans, and the arachnids, which are the spiders with 8 legs, and finally the insects with 6. These are the ones that have instincts developed, first animals to have instincts highly developed, as in ants with their beehives and termites, ants with their anthills and bees with their beehives and termites with their elaborate colonies and different kinds of creatures. Instincts become highly developed here. when we get to the next stage, which are the vertebrates, which are technically known as chordata, because the nerve cord is the important thing rather than just the skeleton. Now I think it's time to tell you another little secret about this thing. I could put this down because I want you to think. I'll take it back to an early stage in the development of this theory where I found a rather disconcerting factor. Since I'm talking about 7 different successive stages, then you would expect each stage to take off from where the previous stage left off. Thus, the very complicated molecules, DNA and virus, is it only takes one step more to get to cells. In fact, some people would classify the virus as living, but it's more or less agreed that the virus is a complicated molecule and not quite reached the cell stage. So that the cell takes off from the most complicated molecule. On the other hand, the animal doesn't begin with the most complicated vegetable. In fact, the animal goes all the way back and starts over again as a one-celled creature. So my concept of a series of things one after another came to grief there, because instead of one after another, it was beginning over again. But then I looked back and I noticed that the most complicated molecules were not made out of the the simplest molecules were not made out of the most complicated atoms. If they were, it would mean radium and uranium and things like that were making the simplest molecules. No. Even the most complicated molecules were made out of the simplest atoms. Hydrogen, oxygen, nitrogen, and carbon. Right up to the DNA. Those are the major, those are the atoms that are used to make up DNA. Never the most complicated atoms. No uranium in your entire physical organism. Well, then I could see the pattern. That it was only the even stages that went back and started over again. And this reminded me of one of the craziest times of my life. I thought I could invent a music composing machine with electronic circuitry. It wasn't like that synthesizer, because the point was to compose the music. Well, I succeeded in getting all sorts of fantastic patterns, and I would dance around the shop. Sometimes I'd get so high on it I could hardly turn it off. But I was not getting music. And the reason it wasn't music was that it was the same whether I played it backwards or forwards. In other words, true music or true composition must have some cumulative build-up, like the plot of a story. It must keep building on what went before so that the denouement incorporates all of what's gone before into one explanation, wraps it up, as it were. Well, I could read that back on the theory of process now and see that each of these stages accumulates what the powers that has been achieved in the previous stages. And this right away makes it quite different from anything that science talks about, or even mathematics, because science and mathematics deal with things that are separate in their own right. That is to say, they're not cumulative. In fact, I've been searching in mathematics to try to find some way of talking about cumulativeness, and it's almost impossible. But nature is using this principle because the plants are based on the molecules, which are based on the atoms, which are based on the particles, which are based on light. So it's cumulative right straight through. But this cumulativeness goes on just as music does by striking out, as music does, announcing a theme. Then the theme is repeated before new material is introduced. It's da-da-da-bump, da-da-da-bump, and then da-da-da-da-da-bump. You're only ready for the complicated thing when the first has been stated and then reviewed. In fact, the review is a way of incorporating what's been learned in this first step. So there we are. The odd ones advance and the even ones recapitulate. There's even some possibility that the seventh, which would be man, recapitulates in an even deeper sense than the odd, even way, because now we've got 2 threes, 1, 2, 3, 1, 2, 3, and then starting all over to incorporate it with the seventh. Now, we're ready for a rather comprehensive look at this whole thing. You see, this grid doesn't really show the way it is. It's sort of an abstract layout, mathematical. But let me show you this other one. Very beautiful, made by someone from Frank Bohr. Barbara Curran made this. And it's going to be a little hard to see it, but it doesn't really matter. The substages are shown in each stage. The second one, we haven't filled them in because the physicists haven't made up their mind about what's going on. The atoms, these are the same as the rows of the atoms. These are the same as the chemicals. The vegetables, the animals, and man. In other words, the process of evolution not only goes through 7 stages, but each one of the stages has to go through 7 substages. And the nature of the stages is sufficiently similar so that you can get information from the substages about what the grand stages are. Now, it's in that way that I was able to fill in, at least tentatively, what man can expect, because we'd like to know what's going to happen to us when we evolve further. And it was that led to the word dominion. You see, I noticed that the dominion principle held, let's say, with the virus, very conspicuously. The virus is the top chemical, and so is the DNA. But the virus has this capacity to go into a cell and change the instructions so that instead of making what it was making before. The cell, let's say it was some hard-working germ or something, but the virus goes in and turns it into a factory for making viruses. Dominion function is very well illustrated by that. Of course, even the DNA has that dominion function because it's the boss molecule and explains and sends out the instructions for the whole, building the whole creature. And don't think of dominion in a bad sense, because if you didn't have this capacity, when you ate chicken, you'd turn into a chicken. In other words, the DNA ensures that you retain your own identity and manufacture yourself.